Hello everyone. Today we are going to be going through how to graph some modulus functions. Now, let's just begin by defining what we mean when we say the word modulus. When we are asked to find the modulus of a particular number, we are essentially being asked to find its absolute value. What this means is that we are finding its magnitude, in other words, its magnitude. So essentially, we are ignoring its direction. We are ignoring the sign out the front of the number. So when we're finding the modulus or the absolute value or the magnitude of a number, we are simply being asked, where does it lie with respect to 0 on a number line without caring for the direction? So if I were to put 0 and -3 on a number line, all this is asking me is how far does -3 lie from 0 on a number line? And we know that it lies 3 units away, regardless of direction. So we do not consider direction over here. So what this means is that if we're asked to find the modulus of -3, well, this will simply be 3. Similarly, if we're asked to find the modulus of -4, this would simply be 4. If we're asked to find the modulus of 2, well, 2 would be here on a number line, and it's simply 2 units away from 0. We don't care about the direction. All we care about is that it's 2 units away from 0. Its magnitude is 2. Alrighty, now that we have an understanding of what modulus means, we can try to determine what a modulus function would look like. The best way to explain this would be to go back to our coordinates. So let's try to substitute in values of x and determine our values of y to graph this first function. So if we were to put in x equals -3 into this equation, then we would get y equals the modulus of -3. Well, as we determined before, the modulus of -3 is simply 3. So your coordinate at this point would be -3, 3. If we put in x equals -1, our modulus of this would just be 1. If we put in x equals 0, our modulus of this would simply be 0. If we were to put in x equals 1, our modulus would be 1. If we were to put in x equals 3, our modulus would be 3. Now that we have our coordinates, we can begin to graph this out. So we know that one of our coordinates will be at 0, 0. That's over here. 1, 1 over here. And 3, 3 over here. Going in the negative x direction, our coordinates would be -1, 1, -3, 3. And this graph would go on, but these coordinates are enough for us to figure out the general shape of the graph, which looks kind of like a V. Now, if we were asked to graph the linear function y equals x, that would look something like this. A straight line with a gradient of 1. By adding the modulus, I'd like you to notice what we've essentially done is we've taken the negative x region of the graph, which is over here, and we have flipped it over the x-axis. So we've flipped it over the x-axis to bring the line over here. This is because our y values in this equation can only ever be positive. We can never get a negative modulus from this equation. Now, let's try a slightly more complicated example. Now, you may remember from your quadratic functions that if you have an equation in the form y equals a brackets x minus h squared plus k, your turning point will always be at h, k. Well, this is quite similar for a modulus graph, only we're not dealing with a turning point, we're dealing with an apex. Your apex over here would be at 6, 1. So this is your h and this is your k. So your apex for this graph will be at 6, 1. Now, the apex, in case you didn't know, is actually the point of the V-shaped graph. So that would be over here for the last graph that we drew. So we know that the apex will be at 6, 1. Again, we have to find our other special features of a graph, including our y-intercept and our x-intercept. So let's go ahead and do that. So if we are to find our y-intercept, we are simply going to make x equals 0. So we would get y equals the modulus of 0 minus 6 plus 1, which would equal the modulus of negative 6 plus 1. And we determined before that the absolute value, the modulus, the magnitude of negative 6 would simply be 6. Adding the 1, we get y equals 7. So your y-intercept coordinates would be at 0, 7. Now let's try to determine whether we actually have an x-intercept for this equation. So normally to find our x-intercepts, we would make y equals 0, wouldn't we? So let's go ahead and do that. So we've got 0 equals the modulus of x minus 6 plus 1. Rearranging this, I am going to minus 1 from both sides. So we get negative 1 equals the modulus of x minus 6. Now, what did we determine before? We know that no matter what value we get in this modulus, if we're taking the modulus, if we're taking the absolute value of any number between these two lines, it will always spit out a positive number. So, essentially, it is impossible for us to get a modulus of a number which is negative. It is impossible for us to have a number between these two lines that gives us a negative absolute value, because our absolute values do not consider direction and our absolute values are always positive. So what this means is that actually there are no solutions to this equation. So we have no solutions to this equation. So we have no x-intercepts. And this makes sense. If we go to graph this over here, then we already know that our apex will be at 6, 1. So let's make 6 over here, 1 over here. And our y-intercept is going to be at 0, 7. So that would be somewhere up here. Let's just put that there. And we know that the general shape of our graph is V-shaped. So it looked something like this. Now, we can also visualize here why we have no x-intercepts, because our graph is an upwards facing V shape. Again, if we were to have simply graphed a linear function, in the negative side, we would have to flip it over the x-axis. This isn't so much relevant for this example over here, but we will see some examples to come where we use that rule. Alrighty, let's try another one over here. And actually, I'm going to change, let's try this one over here. Alrighty, Again, looking at this equation, our apex will be at hk, which over here would be 3, 1. We have to find our y-intercept, so we will make x equals 0. So this would give us y equals negative modulus of 0 minus 3 plus 1. So y would equal the negative modulus of negative 3 plus 1. The absolute value of negative 3 is simply 3, but we have to bring this negative down. So because this negative was out the front of the modulus, this is why we can obtain negative 3 as our calculated number or our calculated term in this area. So negative 3 plus 1 would equal negative 2. So your y-intercept will be at 0, negative 2. Now, let's try and solve for our x-intercepts. So your x-intercept, to find it, we usually make our y equals 0. So let's go ahead and do that. So we get 0 equals negative modulus of x minus 3 plus 1. Rearranging this, I will minus 1 from both sides, obtaining negative 1 equals negative modulus of x minus 3. I will divide both sides by negative 1 to get rid of this negative here, and that would give us 1 equals the modulus of x minus 3. Okay, now this would be a simple equation to solve if the modulus wasn't there, right? So to solve this equation, normally we would simply solve for 1 equals x minus 3. Rearranging for x, we would get x equals 1 plus 3, so x equals 4. But this actually isn't our only solution for x. Now, to illustrate this concept, let's just look at our simpler example that we were working with before. So y equals the modulus of x. If I were to give you an equation to solve, where you had to solve for 2 equals the modulus of x, intuitively by now you should be able to tell that the two values of x that we could have in here would be 2, so positive 2, or negative 2. So your answer here would be plus or minus 2. So x equals plus or minus 2, because the modulus or the absolute value of negative 2 is still equal to positive 2. Now, intuitively, we can tell this, right? But it gets a bit more difficult when we're looking at more complicated modulus equations like this. Now, in case you didn't realize, essentially what we did to solve this equation is we made 2 equations from this. The first being the very simple one, 2 equals x, to get our positive 2 value for x. And the other one was actually taking the negative of what's inside the modulus. So the second equation was actually 2 equals the negative of what's inside the modulus, which is negative x. And solving this for x, you would get x equals negative 2. So this is how we solved for our second answer, x equals negative 2. Now I know we did this intuitively, but essentially this is what we did in our heads to break it down. To solve this more complicated equation, we are going to be doing the same thing. So we took the normal one over here. So we already solved for one of the answers, but solving for the other answer would require us to take the negative of what's in the modulus. So we would take the negative of x minus 3. So we would get 1 equals the negative of what's in the modulus, so the negative of x minus 3. Expanding these brackets out, we would get 1 equals negative x plus 3. Rearranging for x, you would get negative x equals 1 minus 3, which gives us negative x equals negative 2. Therefore, x equals 2. So our 2 x-intercepts for this graph are going to be at x equals 4 and at x equals 2. Our y-intercept will be at 0, -2, and our apex will be at 3, 1. Alrighty, let's go ahead and graph this equation. So our apex is at 3, 1. That will be over here. 3, 1. Our y-intercept is at 0, -2. So that's over here. And our two x-intercepts are at x equals 4 and x equals 2. So x equals 2 is over here. X equals 4. I'm going to have to expand this a little bit just for clarity. X equals 2, x equals 2 would be here. X equals 4 would be over here, giving us the general V shape of our modulus graph, this time being upside down. And again, you should have been able to intuitively tell this by this negative out the front. So the negative out the front over here implies a flip over the x-axis as it does for any other quadratic equation, for example. So labeling these coordinates, our apex is at 3, 1. Your x-intercepts are at 4, 0 and at 2, 0. And your y-intercept is at -2, 0. All right, lovely. Let's move on to another equation. Let's try graphing this one over here. You should be able to tell if we are graphing this without considering the modulus, we are graphing a simple quadratic equation. So let's begin by graphing our simple quadratic equation. When we're graphing our simple quadratic equation, we are solving for the y-intercepts and the x-intercepts. So this graph is quite simple. So we should be able to solve easily for the turning points. So let's do that now. So if we're solving for our y-intercept, we will make x equals 0. So we get y equals 0 squared minus 9. So y equals -9. So your y-intercept is at -9, 0. So let's put -9, 0 over here. Alrighty, finding our x-intercept, we will make our y equals 0. We get 0 equals x squared minus 9. Rearranging, we get 9 equals x squared. Again, taking the square root of both sides, we get x equals plus or minus 3. So your coordinates would be somewhere here. This graph isn't really drawn to scale, but let's just get a rough idea of what our normal quadratic graph would look like. It would look something like this. Okay. But we are not actually graphing a normal quadratic graph. What we've done is we've added a modulus to this. Again, what does this imply? We are taking the absolute value of whatever's in this modulus, whatever's between these two lines. What that means is that your y values that you obtain from inputting any x value here would always be a positive number. So anything that this term in here equals, no matter if it be positive or negative, if we're taking the modulus of this, your y values will always be positive. Now, do we have a region on this graph where our y values are not positive? Well, yes, we do. This entire region over here, our y values are negative, and we know that this is not possible for a modulus graph. So what this means is that we are meant to flip this region in across the x-axis. So we're flipping it over the x-axis, and this graph's shape is actually meant to look like this. And your previous y-intercept of -9, 0 now becomes positive, so it becomes 9, 0. So the graph of your modulus function, so the graph of this modulus function actually looks something like this in blue. So there's your graph of your modulus function. And you've actually got two apexes over here at -3, 0 and at 3, 0. Okay, hopefully this helped clarify some very basic modulus functions. In the next video, we will go on to do some more complicated types of examples. As always, let me know if you have any questions. Otherwise, I will see you next time.